And this function has 2 at x equals -1 and at y equals 1. Also, it has a hole at 2, 2/3. Ready? Coming from approaching 1, opening up, increasing towards infinity. Piece of cake. One thing I don't want to forget. A function can cross a horizontal and or slant asymptote, comma, but never a vertical asymptote. Never a vertical asymptote. So a function can cross somehow the slant asymptote, can cross the horizontal asymptote, but never the vertical, ever. Okay, back here. Sorry,
I'm sorry, why is it an asymptote then if it can cross it?
Very good question. But you understand why it will never cross the vertical one, right? Because the function is undefined there. Okay, so the question here is, very good question, how come that a function with a horizontal asymptote can cross that, right? Remember one thing, the horizontal asymptote doesn't mean anything here in the middle. The horizontal asymptote only says to us that far away, the function will get closer to that number. Far away, the function will get closer to that number. That's all it says. But I cannot graph a horizontal asymptote showing you a little piece here and a little piece here. I have to graph the whole line. And a function can do this. So the horizontal asymptote only says where the function is going here. Does not say anything about the middle. It only signifies where the function is going when x approaches infinity and where the function is going when x approaches negative infinity. Very far away, very far away. Nothing about the middle. Very good question. So now, how will a function look like when it crosses a slant asymptote? As an example. So let's say this is the slant asymptote, whatever. And the function may do this. Because this line doesn't mean anything in the middle. It only simply signifies that very far away, the function will eventually approach it. So in the middle, but I can't, when I graph a horizontal asymptote, I cannot say, here's the horizontal asymptote. I have to graph the entire line. Perfect question, thank you. So back to our graph here. Where am I? So from 1 going up, opening up towards infinity. Then it's coming from negative infinity, crossing at 0, 0, going through, opening down all the time, all the way. So still increasing all the time, still increasing all the time, opening down all the time. Coming from negative infinity, crossing at the origin, going through the open point, and then asymptotically getting closer and closer to 1. So this was our function, y equals x times x minus 2 over x plus 1 times x minus 2. Not this function, but of course he could have done this. So he could have crossed the horizontal asymptote, and he can cross a slant asymptote, but never the vertical because the function does not exist there. Questions for me, please? So this was 11. I'm moving on to 12. Any questions, please? Any questions? Okay, now I finally consider 4.4 complete. 4.5 was complete. It's just the same thing, putting everything together. So we're looking now at 4. Which one we don't cover? We don't cover. So 4.6 is the calculators. Yes, exactly. So the last two sections we have left here, 4.7 and 4.8. So optimization problems and Newton's method. Because Newton's method, it will take a blink. I like to start with Newton's method and then optimization problems. I moved the test. Let me change this. I moved the test with your permission, unless you want otherwise. I moved the test Monday, not next Wednesday, but the following Monday, because I would like you to have that weekend to finalize the WebAssign. So Monday you can tell me, no, I don't want to do that. I already finished. I want to test. Oh, my computer is running out of juice. So it's up to you. I'll do whatever you want me to. But for now, I scheduled it for the 13th. If you want to make a change, you can always tell me, okay? So let's continue with 4.8. Oh, I didn't mean that, but that's fine. So I'm going to open 4.8 and then stop sharing. And then switch the camera, of course. Okay. So 4.8, Newton's method. Okay. So one thing for continuous functions, of course. For continuous functions. Do you remember that theorem that we looked at on the interval a comma b, and we said f continuous on a comma b, and here's the graph of f of x, or of course this. So if f is continuous on a comma b, and f of a, as I graphed it, is less than 0, and f of b is greater than 0, we conclude that there exists a c in the open interval a comma b such that f of c is 0. Anyone remembers the name of this theorem? So if the function is continuous and it changes sign, either from negative to positive or from positive to negative, there must be a point where it crosses the x-axis. There must be a point that is the root, there must be a point that is the x-intercept, or the solution of f of x equals 0. Which theorem was this? Under continuity. If the function is continuous, it cannot jump over 0, in other words. It goes each point, point by point, point by point, point by point, point by point, 0, and then goes positive, point by point, point by point, point next to point, because it's continuous. How did we call that theorem? Anyone remembers the name of this theorem that works only for continuous functions? It goes point by point, intermediate, everything. One next to the other, one next to the other, one next to the other. It's the intermediate value theorem. We are going to use this theorem today to illustrate Newton's method. That's our starting point. Okay, so let's choose an equation that otherwise we will never be able to solve by hand. I cannot solve any of these by hand. I cannot solve the equation sine x equals x minus 1 by hand. I have no clue how to do it. Cosine 2x equals x cubed. 2 to the x equals 2 minus x squared. I have no idea how to solve any of these equations. But Newton's method will help us do that. But by hand, it's not possible. But Newton's method will help us determine the solution with any accuracy you want, 6, 8 digits. So let's choose a problem. One, 1.5, 2, 2.5. Fine, 21. So 21 is arctangent x equals x squared minus 3. Good. Before we work on this problem, we want to discuss and see what Newton came up with. Page 13. So here he said, okay, we have a continuous function, f of x. It has a root, r is the root, or the x-intercept, whatever you want to call it, it doesn't matter. And remember one thing here, we said that this must be a 1 unit interval between 2 and 3, not between 2 and 10, between 2 and 3, or smaller if you want, but between 2 and 3, or 1 and 2, 5 and 6. So this is a 1 unit interval. 1 unit interval. Okay. So let's say this is a continuous function. We use the intermediate value theorem. And we have an open interval, 1 unit interval between a and b. He then said, well, if we start at any of the 2 ends of the interval, start at x0 or x0. Let's say I start at a. That's my starting point. Okay, he said, fine. Create this point. So if this is a, this point has what y value? This point is on the graph of f of x. If the x coordinate is a, what will be the y coordinate for this point? Okay, if this is 5, what will be the y coordinate for 5?
F of 5.
Exactly. So this is this point. I'm going to put it on the side. I'm going to call this point A because this is going to get very crowded in a minute. So point A has coordinates A, comma, F of A. Awesome. Good. So I have this point. And of course, yes, that's what we've discussed all along from the very beginning. I am going to draw the tangent line. The tangent line crosses the x-axis in this point. I'm going to call this point point B. Point B now has coordinates x1. So this is our x0. Here I have x1, comma, 0, of course. It's on the x-axis. And here's my question. We started with x0 or x0. This is my starting point. I obtained a better approximation. So this is the x1. Because x1 is closer to the root. This was 1, let's say. This is 2. But now with x1, I'm much closer to the actual solution that I started with. Perfect. So this point, again, has coordinates x1, comma 0. Now, can anyone refresh our memory? What is the slope of the tangent line at x0? The slope of the tangent at A. This is what we studied in calculus so far. What is this? Yes?
F prime of x0.
F prime of x0. Awesome.